Just a year ago, up to 45 million people were living with HIV, with a 90% mortality rate. Now that's insane. Now HIV is essentially a virus where your cells deteriorate because the virus will latch onto your white blood cells. So the cells that are supposed to be fighting viruses are actually the ones being affected. Now to treat this, we have to use a targeted drug delivery path, while introducing dendritic polymers and nanotechnology. Let me break it down for you. Nanotech is essentially analyzing everything at the nanoscale. For example, if we were all the size of a nanometer, the entire world would fit into one car, a Hot Wheels car. Now the chemical and physical properties of everything will actually change at this tiny scale. And if we harness these properties, then we can solve many different problems, one of which being drug delivery, and that's where those dendritic polymers will come in handy. Dendrimers are these 3D hyperbranch polymers with three main parts: a focal point, interior voids, and functional groups. We're going to be focusing on polyaminoamine or PAMAM dendrimers. Now each time the number of functional groups on these branches double, we move up by one generation, meaning the higher the generation, the more complex the dendrimer. Now PAMAM dendrimers have great water solubility, stability, and oral bioavailability. Since dendrimers are hyperbranched, we can actually really easily modify them based on the generation, coding, and functional groups. For example, they can carry hydrophobic and hydrophilic drugs at the same time. Mind-blowing. Now, we can actually form them in two different ways, one of which being convergent synthesis and the other divergent. Divergent synthesis is where the dendrimer is made from the focal point to the outer branches. This makes it really easier to control the number of functional groups. For example, PAMAM dendrimers have amine, carboxylic, and hydroxyl groups, and these functional groups are based on the functionality of the nanoparticle. For example, hydroxyl groups will allow for the drug to be really easily loaded. Convergent synthesis, on the other hand, is building from the branches to the inner core. Okay, so now we know how dendrimers work and how they're created, but how do we actually load drugs onto them? So first we have encapsulating the drugs into the interior voids. Dendrimers have all these interior gaps because of hydrogen bonding. Now allowing for the drug to be in the blood for a really long time, it will actually increase the stability of the active tissue targeting. So this is why encapsulating them is a really great way to load them. We also have conjugation of drugs onto the functional groups. Now one single dendrimer can actually carry so many drug molecules if we use it this way, and we can target it really, really well. Alright, so now we're on to the really exciting part, which is the combination of dendrimers with HIV. The great thing about these nanoparticles for HIV is that they actually minimize the side effects and can possibly prevent transmission. Normally, HIVs latch onto the host cell and fuses with the membrane. The viral RNA will turn into DNA, which then goes into the host cell's DNA. The mRNA is then formed with protein expressions which will actually cause the virus and cause it to replicate. If we can block these first two steps, we can actually prevent HIV infection. And the functional groups will actually interact with the proteins and the receptors on the host cells. That being said, dendrimers are still under their research stages, so there's certain reasons why they're not fully in use at the moment. First off, dendrimers can actually have potential risks for our environment. Now, some of the positive factors like stability and availability to escape barriers may pose as a risk. The residue or the drug can actually go into the environment during synthesis, and if these dendrimers were to enter the bodies of aquatic life, then the bodies might react to the drug differently, and the dendrimers can actually lose control and release the entire drug at once, which could lead to death. But this is only if the dendrimers actually are exited into the market, which may be difficult because of the game of politics. Now, if there are technological advancements, then there's going to be a jump of production. But if there's hurdles, then the demand of dendrimers will actually evolve at a much slower rate, which will cause them to not actually expand to production capacities. Now, the largest area where dendrimers actually have promise is in medicine. But with constant competing technologies, the companies might not be able to take a risk because they don't want to lose to their competitors. Now, the last factor playing into this rise of dendrimers is the money. Synthesizing and buying dendrimers can range anywhere from $100 to $2,000 just for 100 milligrams. Higher generation dendrimers are a lot more in demand, but their generation directly corresponds to their mass, meaning that the price is really, really expensive. Now, if they were to expand their production, then the prices have to drop, but the only way to do that is to find new materials to make the dendrimers, but those aren't going to have all the pros that these polymeric dendrimers have. Now, dendrimers, they are incredible. They have amazing properties, and they could lead to treating HIV. But at the same time, they have a lot of limitations. But who knows? Sometimes the biggest problems can have the smallest solutions, even if those solutions are on the nanoscale.